For field compaction, soil is spread in layers and then a certain amount of water is sprayed because we have a certain amount. In lab, we conduct the standard Proctor test to find the optimal moisture content, which yields the maximum level of compaction. Then soil compaction is done in layers. We need to control the moisture content and then also consider factors affecting field compaction, which includes the type of soil that we have: well graded, poorly graded, coarse material, fine material, does it have clay or not, moisture content, and compaction factor, which basically means the thickness of lift, intensity of pressure, the external pressure that is applied by the equipment, and the area over which the pressure is applied. This is an example of spraying water on each lift of soil before compaction in field. Let's look at some equipment that are used for field compaction. This is an example of a smooth wheel roller which provides a smooth finished grade. This one is usually used for paving application, for proof rolling of subgrades, and to finish operation of fields, especially when we have sandy or clayey soil. This one is an example of a sheep's foot roller. Compared to the smooth wheel roller, this provides greater compaction pressure and it can be more effective when we have fine grained soil. So this one is basically a drum with a large number of projections. Again, this is very efficient when we have fine grained soil or a clayey soil. This type of roller is suitable for clayey soils. Pneumatic roller, these are suitable when we have clayey and sandy soil. So these are pneumatic rubber tired rollers, and in many cases these are more efficient compared to a smooth wheel roller. The load is applied using several rows of tires, and these tires are, as you can see in the picture, closely spaced. Another group of compactors is vibratory compactors or vibratory rollers. So these ones, they have a different technique. They use vibration to move particles along each other. And these, so when we are using vibration, can be very efficient when we have granular soil. This is not efficient when we have clay or fine. This is effective when we have granular material or clean sand and gravel. It can also be attached to the previous rollers that we mentioned, so we can have a combination of vibratory rollers and pneumatic rubber tired sheep's foot rollers, or even a smooth wheel rollers. It can be more efficient. This slide shows the principles of vibratory rollers. They usually use off-center rotating weights, and that will cause the vibration. Another example, a more advanced compaction technique is dynamic compaction, or DC. This is used when existing surface or near surface soil is poor and it doesn't provide the required engineering properties. It is more effective in granular soil, but it can be used for cohesive soil with caution. So what is dynamic compaction? Dynamic compaction is basically a heavy weight, can be between 2 to 20 tons, dropped on the surface of soil from a height up to 30 meters. So again, it's consisted of a heavy weight that is dropped on top of the soil from a certain height. Preparation: determining the location for phase 1, and then heavy weight is dropped on top of the soil surface, and the impact compacts the soil. So in this example, they will do a secondary dynamic compaction. And remember that dynamic compaction should always be followed with filling the holes that are made as a result of the dynamic compaction. So in phase 2, the location for the drop of the weight is different to cover the whole area. And it's again followed by a secondary technique to fill out the holes and also to compact that soil. So in order to do a dynamic compaction, we need to know how many number of drops are required. It's usually between 5 to 10 drops. And previous results show that additional drops beyond 10 drops cause a very small improvement, so it's not cost effective. Needs to be backfilled and compacted. Again, the degree of compaction achieved at a given site depends on weight of hammer, how heavy the weight is, what is the drop height, and what is the spacing the weight is dropped. This table gives you an idea which type of soil we can actually use DC, dynamic compaction, for which type of soil. As the slide showed you earlier, dynamic compaction is a good option when we have granular soil. So granular deposit, we have an excellent here. Granular deposit with high degree of saturation is good, but if you have low degree of saturation, it's excellent. Not recommended when we have highly organic material. When we have fine material with high degree of saturation, again, not recommended. Another technique is called vibroflotation. Vibroflotation is a technique for in situ densification of thick layers of loose granular soil. So this is again the technique that can work very well for granular soil. The process involves the use of vibrofloat unit, which can be up to 2.1 meters long, This vibrating unit has an eccentric weight inside it and can develop a centrifugal force which enables the vibrating unit to vibrate horizontally. And there are openings at the bottom and top of the vibrating unit for water jets. So it's a combination of. So again, this is an example of a vibro floating, which has the combination of vibration and heads for water. Both of these helps with the movement of aggregate, and then additional material needs to be added to fill out the space that is caused by the vibro flotation. Okay, so now we want to be able to calculate how much material is compacted in cubic yard per hour. So cubic yard of materials compacted per hour, and that's very simple to calculate. We need to know what is width of compaction, how much is the speed of the equipment, the roller, what is the thickness of compacted leaf, and how many passes is required to meet the specification. And then we need to multiply by 16.3 to convert these different units that we have to cubic yard. We never achieve the number that we get from this calculation. There is an efficiency factor. If the job condition is described as efficient or excellent, then we achieve 90% of this number. If the work condition is described as excellent. If it is described as average, then we can achieve 83% of that number. And if it's described as poor conditions, then we can actually achieve 75% of that number. So it's important that you pay attention to job efficiency factor. Let's do an example. Calculate the compacted cubic yard per hour. Cubic yard per hour. If compactor with a 6 feet drum width, so that's our width, travels at 7 miles per hour, that's our speed, over an 8-inch lift of aggregate, that's our thickness of compacted lift, and the test strip indicates 4 passes. That's the number of passes required. Plug in the numbers in the formula that we have: width, speed, thickness of lift, and number of passes, and we have 1,369 cubic yard is compacted per hour. But what is the actual volume? The job condition is just normal or average. So instead of this number, we can only achieve 83% of this. This is average or normal. So we need to multiply this number by 83%. And that is the actual cubic yard compacted per hour. Again, another example, we have width of 4 feet, a speed of 2.5 mile, thickness of lift 8 inch, and number of passes required 4. The job condition is described as average, which means that 83% of the cubic yard compacted per hour will be achieved. So W times speed times thickness of lift divided by P, and then this number needs to be multiplied by 83%. This is the actual material compacted in cubic yard per hour. Now let's look at another example. A proposed embankment fill requires a total volume of compacted soil of 8,500 cubic feet. So total volume is 8,500 cubic feet. That is the volume of compacted soil. The void ratio of the compacted fill, void ratio was volume of void divided by volume of solids. So we want to compact soil for an embankment fill. The total volume of the compacted soil will be 8,500 cubic feet, and it will have a void ratio of 0.7. That's what we want. We have 4 borrow pits that are available as with this information. We have pits A, B, C, D, void ratio of material in each pit, and cost of bringing material from each one of these. We want to see which one is the most cost-effective option. We want to bring soil from these borrow pits, and we want to see which one will be the most cost-effective option. So, for compacted soil, we will have a total volume, which is volume of solids plus volume of void of 8,500 cubic feet. And it needs to have a void ratio, which is volume of void divided by volume of solids of 0.7. From here, we need to calculate what is the volume of solids and what is the volume of void for our embankment. So we have volume of embankment equals to volume of solids plus volume of void, and void ratio of embankment equal to volume of void divided by volume of solids. This is very similar to when we wanted to calculate volume of solids and weight of solids and weight of water in a previous example. We have 2 missing parameters and 2 formulas. So we have volume of solid plus volume of void is 8,500 cubic feet. We also have volume of void divided by volume of solids is equal to 0.7. 2 missing parameters, volume of solids and volume of void, 2 formulas. We rearrange the second formula. Volume of void is equal to 0.7 times volume of solids. And instead of volume of void here, we put 0.7 volume of solids. If we do that, now we have a new formula which says that volume of solids plus 0.7 volume of solids is equal to 8,500 cubic feet. This is 1.7 volume of solids So 1.7 volume of solids is equal to 8,500 cubic feet, which means that volume of solids is equal to 8,500 divided by 1.7. And that's equal to 5,000 cubic feet. Then you can calculate volume of void as 8,500 minus 5,000 or as 0.7 times 5,000. And you will get 3,500 cubic feet. So for our embankment, volume of void is 3,500 cubic feet. Volume of solids is 5,000 cubic feet. Why do we need to do this? Because this will be constant. Because the question told us, assume that the specific gravity of soil solids from all of these pits are the same as embankments. So assume the specific gravity of soil solids to be the same at all pits. What does that mean? It means that we need to bring the same amount of solids from all of these pits. Because they have different void ratios, we cannot use the total volume. We cannot use the 8,500 cubic feet because they all have different void ratios. But we can use volume of solids. In our embankment, we need 5,000 cubic feet of solids, which means that we need 5,000 cubic feet of solids from each one of these pits. So, for example, pit A, we need to have, let's look at pit A. We need 5,000 cubic feet of solids. Void ratio is volume of void to volume of solids. So if we need 5,000 cubic feet of solids, then volume of void is 1.08 times 5,000. So volume of void is 5,400 cubic feet. So for soil A, we still need to bring, volume of solid is the same, 5,000 cubic feet. But since void ratio of A is 1.08, it means that volume of void will be 5,400 cubic feet. So our total volume is 54 plus 5,000, which is 10,400 cubic feet. So that's how much material we need to bring from pit A to make sure that there is 5,000 cubic feet of solids to be able to do the 8,500 cubic feet for the embankment fill. We also know that it will cost $5 per cubic feet, so the total cost is 10,400 cubic feet times $5 per cubic feet. So the total cost to bring material from pit A for our embankment fill is $52,000. Now we're going to do the same thing for pit B. Again, we need to have 5,000 cubic feet of solids from B. For B is 0.85, which is equal to volume of void to volume of solid. So volume of void for pit B is 85 times 5,000, which gives us 4250 cubic feet. So now for soil B, again, volume of solids is 5,000 cubic feet. Void ratio is 0.85. From here we can calculate that volume of void is 4250 cubic feet, which means that the total volume is 5,000 plus 4250, which is 9250 cubic feet. That's how much material we need to bring from pit B to make sure that we have enough solids for our embankment. This one, the cost is $8 per cubic feet, so the total cost is $74,000. You need to repeat this for pit C and D. Again, for both of these, for pit C, and pit D. Volume of solids is still 5,000 cubic feet. Void ratio in pit C is 0.87. For D is 0.80. We do the calculation for volume of void. Here it's going to be 4350 cubic feet. And here it will be 4,000 cubic feet. So we have a total volume from pit C as 9350 cubic feet. Cost is $9. And then here we have volume, total volume of D is 9,000 cubic feet. Cost is $12. So we have and then we can compare the results and see the most cost-effective option is to bring material from borrow pit A. Exercise number 3, it's from compaction. So we have the results from laboratory results of a standard Proctor test. We have volume of mold. So we have this mold. Volume of mold is 1/30 of a cubic feet. And that's equal to volume of compacted soil. We compact our soil in here. And we also have weight of moist soil. So weight of moist soil is weight of soil, compacted soil in here. So we also have weight. This will be volume of compacted soil. And this is weight of our compacted soil in the mold. When you divide weight by volume, you can calculate moist unit weight. So moist or wet unit weight is equal to weight of compacted soil divided by volume of compacted soil. So, for example, look at trial number 1. Weight is 3.82 pound. Volume is 1/30 of a cubic feet. We will have 114.6 pound per cubic feet. Then we need to calculate dry unit weight. Gamma D, which is equal to gamma, this is gamma, divided by 1 plus water content. So it's going to be 114.6 divided by 1 plus moisture content is 10% or 0.1. That will give us so that's trial number 1. You need to repeat that for trial number 2, 3, 4, 5, and 6 to complete your table. When you have all of the numbers that you need, you use these 2 rows. Water content is your x-axis, and dry unit weight or gamma D is your y-axis. You make your curve and then find peak of your curve that gives you optimum water content in percentage that yields maximum dry unit weight, which is also the maximum level of compaction.